Okay, looks like we've started the live stream, so we can start this session on fuzzing. Welcome, everybody. Good morning to everyone, or afternoon, evening, night, depending on where you are, but I'll stick to the Los Angeles time schedule. Welcome to this first session of the technical track of ISSTA on the subject of fuzzing. We have three very interesting talks coming up for you. I just want to iterate how this will work. The speakers will give a talk on the Zoom session. And if you have any questions, please feel free to ask them in the Slack channel. So if you haven't joined our Slack yet, please do so now. The first talk will be presented by Andrea Fioraldi from Sapienza University in Rome. And it will be on the subject of WISE, the automatic gray box fuzzing for structured binary formats. So Andrea, if you want to go ahead and share your screen.
And Roddy, just sorry to interrupt, just 1 second. Right now we'll mute everyone and they cannot unmute themselves. And so I just wanted to let you know about that.
Yes, that's why people should ask questions on Slack. And at the end of the talk, I will read out those questions for you. Andrea, you're still muted.
Okay, do you listen me? Hi to everyone, I'm Andrea Firaldi, a master student from Sapienza, and today I'll talk about WISE, automatic gray box fuzzing for structured binary formats. I'll start with a bit of overview of fuzzing. One of the most used technique of fuzzing, format-aware fuzzing, that is based on an input formal model, and the fuzzer generates these cases following this model and look in the program for caches, of course. And you can look some work in past working literature that follow this approach. There are still known problems in this approach that are, of course, if you don't know the structure of the input, you can write a model. You may fail to find bugs if you generate only valid inputs, and bugs are related to invalid inputs in the parser. Sometimes in programs, the parser implementation doesn't strictly follow the specification. Of course, the models are written by humans, and so this is a process that takes time. And always, due to the model is written by a human, there can be mistake that make the fuzzing ineffective. To deal with this problem, and one approach is to automatically learn the model from the implementation of the parser, and to not always generate valid inputs. Several works try to do it, and most of them use data flow-based approaches like tape tracking to learn an approximated model of the input format. Coverage-based fuzzing is another approach that is widely used in these days, that found thousands and thousands of bugs, and is based on mutation, on generation, and basically the fuzzer mutate a test case and look not only for crashes, but only if this test case trigger a new part in the program, a new coverage that was not seen before. Common problems are that the mutational operators are generic, and so the fuzzer fails to explore deep paths because most of the inputs are generated invalid. And if the fuzzer reach deep paths, they are not stressed. They're stressed a few times, so find bugs in these paths is hard. And there are also roadblocks like multi-byte comparisons that are hard to bypass for a generic mutator. To deal with the first problem, in the recent times was developed structured fuzzing, that is the join of the two previous techniques that I explained. Basically, the input formal model is used not to generate the input from scratch, but the test case is ports, and it is mutated using the model. So it's a better version of coverage-guided fuzzing that generates valid inputs. And several works, most important for our case is FLSmart that try to implement approaches based on structured fuzzing. And for roadblocks, several works were done to bypass them, most notably using concurrent execution, sensitive feedbacks, and again, approaches based on data flow, like approximation or time tracking itself. At this point, you may note that this type of analysis based on data flow approaches are common for both bypassing roadblocks in fuzzing and reconstructing the input model in the format-aware fuzzing. So this come our idea. Maybe we can reuse some technique that used to bypass roadblocks to do also structure-aware notations in coverage-guided fuzzing. We took a recent work that is Red Queen that addresses the input-to-state magic byte comparisons. And basically, it approximates time tracking, doesn't use time tracking, looking for pattern in comparison and in the input, then mutate the input, generating an input that is equivalent in coverage, but much higher entropy, so that it can observe the pattern in the input, substitute it, and do not a lot of guesses because the entropy is high. And Red Queen also individuate checks and checks and patch out checks and checks to do effective fuzzing. Another work based on Red Queen tried to address the mining of the specification in coverage-guided fuzzing, that is Grimoire, but address programs that use parts the inputs into abstract syntax tree or something similar like programming languages parsers. But of course, not all programs in the world are of this type. For instance, there are the chunks-based programs that are like the PNG file format parser in the picture that are based on blocks and chunks that are directly mapped to structures from the input. And so we decided to address the problem of learning a model, do something similar to structured fuzzing without the model, and both bypass the roadblocks at the same time. Because we noticed that in this type of programs that use chunk-based formats, there are a lot of validation checks over fields of the chunks, and maybe we can use it to get some insight about the format itself. So our idea is that we may use the comparisons instructions that are related to validation checks instead of the memory access information that previous work in protocol reverse engineering used, and to get insight about the format. We also talked about that maybe we have to do it during the mutation, not as a pre-processing stage, because we can get wrong, and if we learn a wrong model, if we do it during the mutation, we can do a better guess next time. So we implemented our prototype that is Vide, that is based on FL. It's based on FL QEMU, because of course, if we don't have the information about the input format, probably we don't have the source code. And we don't use time tracking like Red Queen. We use an approximation that is more sound. And we implemented on top of that some structural mutation that are inspired by FLSmart. There is a previous work about structured fuzzing that use a model written by a human. Our solution is divided in two stages. The first is the surgical stage that does the taint analysis approximation, bypass the roadblocks using input to state, fix the checksum, and also place what we call tags alongside the test case that are the information that we extract from the execution of the test case. And then there is a structural weight stage that is basically the mutator. There it is the FL mutator and with our structural mutations alongside. Our taint approximation is based on a simple observation that we can reduce the deterministic stage FL with a bit flipping. Bit flipping each bit in the input and observing how the operands in comparison change. So with this observation, we can relate each operand of comparisons with bytes in the input. We use this information to detect checksum and using these heuristics. And we place for each byte in the input what we call tag. The tag represents the validation check. The tag contains the comparison ID of the most important comparison affected by this byte, a timestamp because we define a total order between comparison based on the first time that the comparison is executed. The parent comparison that is the last comparison in time that affect the input, because of course a comparison may not affect the input. And we also maintain the number of bytes that are affected by this the same comparison. If this byte is protected by the checksum, and other information like if this byte is itself a checksum field, which operand of the comparison is affected, and other information needed for the mutation. Of course, you might note that a byte may affect multiple comparisons. So we have to select what is for us the most important comparison, the validation check comparison. We prioritize if, of course, the comparison is a checksum field, because this is a variable information and for the checksum patching. Then we prioritize if the comparison is a period error in time, of course, because the validation checks are done earlier in time in the program. We prioritize if the bytes that influence the comparison are low, because of course a comparison is affected by many bytes in the input is not a validation check, maybe for instance an hash or a checksum, not the field checksum field, the other part of the checksum. And we fixed also the checksum, like Red Queen, we do it eventually. So in Q, we have invalid test case until they enter the first stage. We do a topological sort to handle nested checksum and unpatch false positive, detecting if they are false positive during always the first stage. Now, talking about the mutator, we locate field using the tag, of course. So we don't locate field and chunks in the first stage, but we just place tag, and we locate fields and chunks and during the mutation. The fields are located like group of bytes with the same tag, but also a group of tags that are recognized pattern. Like for instance, the pattern number 2 is a big endian comparison. So we locate fields in this way using common patterns, observed tags. And we locate chunks, observing that most of the times in chunks-based program, the fields are validated one after the other. And there are a few exceptions that we handle, like checksum. And for instance, in the input, the algorithm will pick a random tag. So what we call chunks can be also sub-chunks in the real specification. We go again to the next block if the timestamp is greater. Do it again in this simple case. And we look for the parent tag in case that, for instance, for checksum, also if the location of the field is at the end, may be done earlier, because if the checksum is invalid, the program doesn't lose time doing validation of fields in an invalid chunk. And with some probability, not always, we take untagged data that is not affected by comparison, because sometimes it's interesting, sometimes not. And on top of that, we define some mutation inspired by FSmart, addition, deletion, and splicing. Addition just take a chunk from the current input, another chunk from another input in Q that has the same parent tag in the first block, and add the second chunk before or after the chunk in the current input. Deletion is just a deletion. And splicing is that we take a chunk from the current input and another chunk from another input in the queue that have the same comparison ID in the first tag, and swap these chunks. We evaluated these approaches. Of course, these heuristic are not, there can be more heuristic based on validation checks to reconstruct chunks. And we evaluated our approach against other fuzzer that target roadblocks on chunk-oriented programs, and also against FL-Smart. We found new bugs using VIDES on our widely used programs, and also evaluated the role of our structural mutations versus roadblock bypassing. We found that against the generic fuzzers that target roadblocks like Eclipser, FR++ compare coverage, and our basic NFL, VIDES can be a huge improvement in terms of coverage, like shown in the paper. And against FL-Smart, we saw that sometimes VIDES is performed quite similar in coverage to FL-Smart, and sometimes it's interesting to see that VIDES can outperform the FL-Smart. This is due to the fact that some programs pose different type of inputs, and typically the input model given to a fuzzer like FL-Smart is about one single input format, like in FMPEG, FL-Smart were fed with the ABI input format, but VIDES can learn and mutate different type of inputs, so can cover much more input space. We found several bugs on when you use this program, like caps and obj dump. And we also evaluated that if we remove the tags-based structural mutation from VIDES, the fuzzer is decremental. Is not the performance is not like VIDES with tag mutation enabled. So it is a real improvement in terms of coverage on chains-based programs. Our future direction are to use time tracking for large inputs. Of course, after a certain threshold, bit flipping is not anymore a great idea. We want to add more chunk location heuristics, like from previous work on protocol reverse engineering, and we want to port the technique to other operating systems, and this is trivial because it's completely operating system independent. Thank you for listening to this talk. The fuzzer source code is open source at this link, and thank you all.
Thank you very much, Andrea, for this nice talk. I'm sure everybody is clapping really loud from their respective living rooms to you right now. I see some clapping hands appearing in the chat. So if you have any questions, please ask them on the Slack channel. For now, let me start by asking a little clarification. On the last slides of the evaluation, you were showing some graphs about how WISE was performing. Can you clarify what's on the X and Y axis? I think X is presumably time and Y is some coverage measure, or? Andrea, you're muted.
Okay. Of course, I went fast due to timing, but of course, the x-axis is time, hours, over 24 hours, and the y-axis is coverage.
Okay, block coverage or?
Block coverage.
Okay, thank you. We have a question on Slack from Rohan Padilla. The question is, does your technique produce a specification of the input format, for instance, with a peach bit, which can be used to power other structural users?
Doesn't produce it because, as I said, we do it online during the mutation, so that if we do not sound guess, we can do better the next time. So the reconstruction of the chunk and fields are done for each mutation. So we can, it's almost every time different, so we can save a model from that.
Okay, thank you. Any more questions? Oh, I see a question on the Zoom chat. Does your technique produce a Oh, that's the same question. I'm sorry. Then I think we can move on to the second talk. Let's thank Andrea again.
Okay, thank you.
So for the second talk, we'll have a video by Yuki Chen from Singapore Management University on the subject of active fuzzing for testing and securing cyber-physical systems. So here we go.
I'm Yuki Chen from Singapore Management University. Today I will give a talk about my paper, Active Fuzzing for Testing and Securing Cyber-Physical Systems. At first, I will introduce what is cyber-physical systems. As name suggests, CPS can be divided into two parts, the cyber part and the physical part. The cyber part is the distributed software components, and the physical part is physical process. From the graph, we can see these two parts are intertwined. The cyber part will get the sensor reading as the input and control the behavior of actuators to influence the physical part. Then these are three examples of CPS. The first one is the water treatment plant. The second one is the smart grid. The third one is the autonomous vehicle. CPS are commonly used in the critical area. The threats of CPS will cause significant consequence. These are the examples. These are the real threats of CPS. And these threats have motivated research into countermeasures. For example, anomaly detection, fingerprinting, environment-based monitors. However, assessing the different countermeasures for CPS is not always straightforward because of the need for a realistic set of attacks to evaluate them against. We have a new issue here. Where exactly should such a set of attacks come from? Typically, the attack set is constructed by some experts or from a hackathon, which takes a large amount of human resources. Then, in order to solve this, I will present Active Fuzzing, an automatic approach for finding test suites of packet-level CPS network attacks. The basic idea of our approach is simple. Once we get the fuzzer, we only need two inputs. The first one is the current network traffic, and the second one is the attack goal. Then we can use our tool to generate the attack, which can manipulate the network packets to achieve the goal. In the following, I will introduce our case study and show you how it works with one example. Okay, this is our case study SWOT, which means Secure Water Treatment Testbed. It is a scaled-down version of a real-world water purification plant, which is located in the ISSTA lab in Singapore University of Technology and Design. This is the system overview. From this figure, we can see it is a complex real-world critical infrastructure testbed with lots of sensors and actuators. So you can find a lot of pumps and wells in this figure. Then I will show you one example of the attack generated by our tool. This graph describes the relationship between some interconnected components across the first three stages. The attack goal is to overflow tank LIT-101. These actuators are related to the tank level. Once we set the goal, our tool will manipulate the packets to open MV101 and close MV201, which are both valves, and close P101. Then water will flow into this tank. If we achieve the goal, you can see what will happen But we cannot always do this because it takes around 2 hours to clean the water. So typically we just set a threshold, and if the sensor value reaches the threshold, we think we attacked this sensor successfully. Then I will introduce the network architecture. Due to the time limitation, I only introduced the level 0 here, which is the lowest level of SWOT. Network attack in this level may change the behavior of actuators directly without dealing with the logic of the PLC and maybe some defense mechanisms in the higher level. Then I will implement my intermediate attack between the PLC and the remote I/O. This connection is in the level 0. Okay, after we implement my intermediate attack, we can get the network packet like this. So how to deal with the packet is a new problem. Luckily, we can use the tools such as Wireshark or Scapy to dissect the header information of a level 0 SWOT packet. Because SWOT implements the Common Industrial Protocol over ENIP protocol. After dissection, we can get the payload of this packet and the corresponding IP address. Actuator commands are encoded in the payload of this packet, but you will see it's still a very long series of numbers. We still do not know how to manipulate this packet. So we need a model to help us to figure out the relation between the sensor value and this number. Then I will show you our assumptions and the limitations. We need to train a model under these limitations. We do not have a pre-existing dataset. We do not have a priori knowledge about the meaning of network packets, and the time is limited. However, we should have the assumption that we can get access to the level 0 packets and observe the sensor value. Otherwise, we cannot manipulate the packets, and if we cannot observe the sensor value, we do not know whether our attack is successful or not. This is the overview of the training. The basic idea is that we train a model based on a small number of data and improve the model based on the living data from the system. In the following, I will introduce what is the prediction model and why we have to do this. Okay, this graph is the prediction model. From this graph, we can see the prediction model can predict the sensor value or the change of the sensor value based on the network packets. There are 16 types of packets in 4 stages. We combine all of them and get the feature vectors with a long series of 0 and 1. So the number of potential combinations is huge, which also shows that if we randomly flip the bits, it is hard to change the targeted sensors. And we use 2 kinds of models here. One is the gradient boosting decision trees, and the other one is the linear model. We use the linear model as our baseline here. Both models can be integrated with existing active learning frameworks for regression. So if we have the prediction model, we can manipulate the packets offline and find out what will happen. And then we have a new question. How long the attacker must spend pre-training on normal sensor readings? Okay, this is the result. These numbers are R2 scores of linear and GBDT sensor prediction models after different amounts of pre-training time. So the number is higher, the result is better. So after 3 hours, we can see GBDT outperform linear model in most cases. Regarding the pre-training time, we fix it at 14 minutes. because our models show some positive correlation here. But you may find some scores are still low, but this will allow us to assess whether active learning is still effective when applied to cases that lack a good pre-training model. Once we have the pre-trained model, we need to do is to test and improve the model. So we have to add new samples and observe the new sensor values and retrain the model. We use two algorithms here to select new samples. Since it is an online learning, so the idea is that we will flip a certain number of bits based on the current network traffic and find out the cases may maximally change the model itself or maximally change the sensor values based on the existing model. Then I will implement my in-the-middle attack to replace the current network packets and observe the new sensor values. Afterwards, I will answer the following two questions. How long the attacker must learn spend active learning? Why we have to do this? Why not just train a model with a large amount of time? Okay, we should answer the first questions. From the table, we can see once pre-trained on 14 minutes of data observations, attackers can accurately predict SWOT sensor readings after 10 to 45 minutes of active learning. And we can see typically the tank level is hard to predict, so it takes longer time. Before solving the second question, I would like to introduce how to discover attack. The first step is to sort the features based on feature importance. In the following, I will introduce what is feature importance. The second step is to define a suitable objective function for prediction value. For example, if we want to overflow a tank, the objective function for this tank is the tank level itself. Then we generate a candidate by flipping fixed number of important bits to maximize the objective function. In this step, we should search the bits from most important features first. Since it is online learning, we should finish all this in a short time, otherwise the current net traffic will change. Once we find the strategy to change the network packets, we should manipulate the packets in the real system. This is the concept of feature importance. We just assign a score to input features based on how useful they are at predicting our target variable. Then I will solve the second question, why active learning is essential. We use the same example here. We try to overflow tank LIT101. Now there are two GBDT models of LIT101 here. The first one is the pre-trained 14 minutes plus 10 minutes active learning. The second one is pre-trained 90 minutes without active learning. The horizontal axis here is the index of the features. As I mentioned, we should use this model to find the critical features to discover the attack. Otherwise, the time is not enough if you just search, for all the features. So through observing, I know these three features will influence these three actuators. So we will find the first model find all the critical bits. However, the second one only find 591, which is related to M101, and you will find there are a lot of features with a higher importance than this. But there is one issue, so we know the R2 score of both models are larger than 0.9. So through this experiment, we know that R2 score only represents the correlation. Only through active learning can you find the real critical bits. In the final, I will find which model and active learning setup is most effective for attack discovery. In the table, we calculate the successful rate by running our active FASTA 1000 times with the given model. Then we record the percentage in which the modified packet would cause the physical state to cross a safety threshold. We can draw a number of conclusions here. First, since the search space is huge, the successful rate without a model is almost zero. And as I mentioned, if we do not use selective learning, the successful rate is very low. And then I compare the performance between the linear models and the GPDT models. And we can see linear models are not expressive in general, and the GPDT models outperforms linear models. However, like the linear models, GPDT models also struggled to attack the LIT sensor values for a small number of bit flips. But you can see it can attack them all once the restriction is lifted to 10-bit flips. One more issue is that we can see the successful rate for LIT 301 is low for all the models. The reason is simple, because this sensor is involved in lots of processes in the system, which means we should change more commands to attack this sensor. This is the evaluation highlight. Through the experiment, we prove that L2 fuzzer is effective at identifying critical bits in payloads and can lead to significantly higher successful rates in attack discovery. And this is the take-home points. In this paper, we propose a black box approach for automatically discovering packet-level network attacks on real-world CPS. And this tool doesn't need a pre-existing dataset, prior knowledge about the meaning of their payloads, and a large amount of time. So we evaluate our method on a real-world critical infrastructure testbed and prove active fuzzing is essential. And that's all. I'm open to any questions you have. Thanks.
All right, thank you very much, Yuki. I see we have one question on the Slack chat from Lingming Zhang. The question is, will the proposed model and current findings still hold for the other types of CPS systems rather than the specific studied SWAT system?
It's like whether the method is general, right? Actually, I think this one should be general. So the point is you should find the right prediction model, and you should find how to change the network packets. And you have the targets, and you find a way to change the network packets, and you can use active fuzzing to do this. Since active fuzzing is based on the framework called active learning, and I propose the one active learning method, and you can use this, for all the different kind of CPS. So the problem is you should find the right object function and the right way to change the network packets.
Okay, that was clear. Thank you. I have a question myself. I was wondering, you are fuzzing the sensor readings. You're fuzzing the network packets. And I was wondering if it's also interesting from a different perspective to fuzz the sensor readings. Like if you're not looking at having an attacker in your network, but you're trying to test the quality of your system, and is there any sensor readings in which like a bad scenario could happen? Do you think this is interesting at all, or are there better ways to test this?
I think it's interesting. Actually, our method is not really to fuzz the actuators. It also try to change the sensor values. So so in this case, so you do not know the meaning of these packets. So for these bits, you change these bits, it will influence the actuators. But somehow you will find that this bits is related to the sensor value. For example, this bits may means that the alarm, for one certain sensor, and you change these bits. Actually, you change the sensor value, and it will raise an alarm. but you will see from the system is like the accuracy will change. So you know my point. So even though you change the sensor value, it will influence accuracies.
Right, right. Any other questions? All right, then let's thank the speaker again.
Yeah, thank you.
And we'll continue with the third and last talk of this session by Björn Mattis from Helmholtz Center for Information Security in Saarland, Germany. Björn will tell us about learning input tokens for effective fuzzing. And I'd also like to point out that for this paper, the authors also sent in their artifacts, and they were evaluated by the Artifact Evaluation Committee, and they received the Artifacts Evaluated Functional Badge, which means that the quality of the artifact is good and that the reviewers managed to reproduce some of the results from the paper. And apart from that, they also received the Artifacts Available Badge, which is a separate process. And that simply means that the artifact is available. Should you be interested in it, you can click a DOI in the conference program and have a look at the artifact. So with that, please take it away, Björn.
So thank you for the kind introduction. I hope you can hear me. Today I will tell you about running input tokens for effective fuzzing. And first I will tell you why fuzzing is great, then why fuzzing with fuzzing complex programs or complex formats is hard, and why we still need it. And then I will tell you how our research tries to make this better and easier. So, fuzzing, raw numbers. So Mozilla is currently using fuzzing day and night, and even other companies are using this day and night to fuzz their tools, their software. And usually what I fuzz are, well, different modules of the software, like the bitmap converter, the bitmap presenter, HTML presenter, things like that, JavaScript. And they found a lot of bugs in the last few years with fuzzing, thousands of bugs, even though there are lots of manual tests written. And the question is, why does this happen? Well, fuzzing is fast, automatic, and has small human bias. And especially the last part is important. So a fuzzer usually does not interact that much with a human, meaning that you cannot bring too much of your developer view into the testing process. And this is great, because then the fuzzer can generate inputs that actually are different from what the human would think could break the system. So let's get a little bit more into detail. A fuzzer generates some random input, gives it to the program under test, and yes, most of the time, those inputs are accepted by the program. But for some inputs, actually, when given to the program crashes, which is bad. But actually what we want to have while fuzzing, because then we can debug the program and fix the bug. Now the thing is, programs are not just a large blob of software. They are more divided. So they have some program logic, and they have some input validation phase, some parsing phase beforehand. And this is bad for random fuzzers, for fuzzers that have no knowledge about the input format. Because if you give the input to the program, then it will get rejected by the parser and doesn't go to the program logic, meaning that you will never test the actual part of the program that you want to test. Of course, you want to test the parser, but more or less most of the time you also want to test the program logic. At least I hope so. This means that you need to give the fuzzer some information, how the input format looks like. You give it to the program, and yes, you get to the program logic, and for any reason the program might crash. So this means for complex input structures, we need syntactic fuzzing. So the fuzzer needs to know how the input format looks like. You can either tell the fuzzer by defining the input format, but then you introduce human bias. So you thought, can't we do this somehow automatically? Can't we figure out how the input format looks like and provide inputs that actually conform this format? And so we presented pfuzzer last year at PLDI, parser-directed testing. And I will give you some introduction to pfuzzer so you understand our new approach. And with pfuzzer, we started, when we start fuzzing, we start with some random input, just one character. We give it to the program, and yes, likely the parser will now tell us, okay, I don't know what this input is. But before rejecting this input, the parser needs to check what it actually expected. So the parser expected the digit on alpha at the beginning. And now what we can do is we can look at all those comparisons that were done on the wrong character and replace it with a correct character. And suddenly our input goes through the parser. And arguably, an input with one character isn't too interesting. So what you can do is you can also extend your input with another character and see what the parser does now. And yes, it gets rejected again. But now the parser would check and see, okay, there should be a minus or a plus. But it isn't. Now, pfuzzer will figure this out and then replace the x with a plus, for example, and goes on. Well, now the input is not finished. So we need another character. And let's randomly append another character. And by chance, this was a 0. So to speed things up, the parser now accepts again the input, and we have full input that conforms the input format and is an expression. So that's great. The only problem is, well, this kind of parsing, this only holds for quite easy parsers, let's say. So if the parser gets more complex and you have an input, this input usually first goes to a tokenizer. A tokenizer is some part of the program that converts the actual characters, the actual input strings and the parts of the input string to internal representations, to some tokens. Those could be enumerations, enums. This could be any other values. This could be integers. And those tokens are then given to the parser. The parser knows what to do with the tokens, but for an outsider, it isn't fully clear what those tokens mean. They have no actual meaning outside of the program. So let's go back to our code, and I extended it with a tokenizer. As you can see in the left code part, there's now a tokenizing function, and this tokenizing function accepts a character, implicitly converts it to some token, depending on which character it just read, and then returns it to the parser. And if the token is not known, well, then it tells you, okay, this was an invalid token. I have no clue what the string means that you just gave me. And then the parser makes sense of this token that it just got, and also checks whether this token is expected at this specific position. And only then it would go on parsing. So why is this a problem? Well, in pfuzzer, we use dynamic tainting to actually find out which comparisons were done on the input. So let's have a look at this dynamic tainting procedure. Let's say we have this input x plus 0. Well, if we give x to the program, then we would see, okay, x is compared against digit and alpha. We wouldn't see anything more, because dynamic tainting means you only have the direct data flows. But the tokens that are returned from the tokenizer are indirectly generated. So there is no direct data flow between the token and the input character. This means we wouldn't see the comparisons in the parser, but those are the valuable comparisons. Those are the comparisons that we want to have to go deeper through the parser. And you can see this better when looking at the comparison of plus. Because now if we compare plus, you will see, okay, there are comparisons against digit, alpha, minus, and plus. So the tokenizer would check all options, or all strings, all tokens it accepts, and would accept all of them. But only the parser will tell you, okay, at this position, at the second position after this x, you can have a minus or a plus. So this is the information we want to have. And that's why we extended the dynamic tainting engine of pfuzzer to also handle those implicit information flows, but only the implicit information flows where a token is generated. So you have some heuristics where you have typical tokenization patterns, and we apply those heuristics to find out which code parts actually involve tokenization and then contained the different tokens that are generated in the tokenizer. Why don't we taint all implicit information flows? Well, then more or less everything of the program would be tainted. So you don't want to do this. You just want to have very specific implicit information flows to be tainted. And yeah, if we do this, then we would also see, of course, for our 0, that this is compared against digit, and also in the parser, it would be compared against digit. So that much for the dynamic tainting. But there's even more to this. We also have to change the way how we iteratively create a larger input. Well, we start again with a random input, as we do with pfuzzer, but this time we would only see the comparisons in the tokenizer. This is good and bad. And of course, the input would be not accepted by the tokenizer. So what can we do with this information? Well, at the moment, we cannot do much. First of all, we can replace our end character with something different, something the tokenizer would accept. So we can replace it with digit, an alpha, a minus, or a plus. And if we do this and replace it, for example, with an alpha, like before, then we would see, okay, now we can go through the tokenizer to the parser. And then we see comparisons. Our token that we got from our tokenizer is now compared against t-digit and t-alpha, which is somehow great, or maybe not. Because, well, what does t-digit mean? What does t-alpha mean? It has no meaning outside of the program itself. So we need to give all those tokens some meaning. And, well, of course, this input is accepted, which isn't too important at this point. But what we can now do is, we also know what the tokenizer, which comparisons are done in the tokenizer. We knew this from our first step. So we replaced our end character with an X. We could have also replaced it with some digit or some minus or a plus. And if we do this, give it to the program, then we can find out, after checking each and every character, what each and every character means regarding tokens. So A to Z means it's an alpha, 0 to 9 is a digit, and minus and plus are for the tokens t minus and t plus. And this is particularly interesting if you go on. So we have our X was correct, but we want a larger input. So we append a new random character, and even more importantly, at this point, we do not only append a random character, we append a random token. If we just append a random character, we would see all the comparisons in the tokenizer again, but we already know what the tokenizer is doing because of the token mapping. So it isn't too interesting for us anymore. So we append a new random token. And now we can see, well, this token was obviously not correct, but our token is now compared against t minus and t plus. If we would not have the token mapping, would now be stuck, because what does t minus and t plus mean? But because of the token mapping, we can now say, okay, at this point, apparently we can replace our 3 with a minus or a plus. So let's just replace it with a plus, and we go on. Okay, like before, like with pfuzzer, our input would now need another character to be appended. And to short things up, luckily we append a 0, so some correct token. And yes, now we have some valid input that actually surpasses the parsing process and would now go on to the program logic that I have not shown in the slide, obviously. So what do we do with all this information? We have the tokens, we have the sample inputs. What can we do with this now? Well, we can give it to some fuzzer that is much faster than our fuzzer or our learning step, because with all this dynamic tainting and learning of inputs, learning of tokens, it takes a lot of it takes some time to learn this information. If we give this information to some fuzzer that can make use of a dictionary built from tokens and some sample inputs like AFL or libfuzzer or your favorite fuzzer, whatever you like to have, then you can generate some inputs and give them to the program under test. What you could also do is you can wait for FSE and look at Mimit, our new paper, which can also make use of those tokens and sample inputs and create grammars from those. And if you have a grammar, well, then you can go on and apply even grammar fuzzing. And another interesting point is, even if you have even if in the sample input some features are not present, like there is no minus, there are no capital letters, even then it is possible for the fuzzer to generate those features just because the tokens are also there. So the fuzzer can make use of the tokens and then replace different parts of the input with other parts. Now for the evaluation, there are two things we wanted to find out. The first thing is tokens. So how good is our token extraction? And we compared it against string extraction. So we took the LLVM bitcode of our program under test and compared it against the dynamically extracted tokens LFuzzer extracted. And we thought, well, with our string extraction, we would find more or less all tokens. But for TinyC and ZJSON, we found out this is actually not true. Their LFuzzer is actually able to generate or to extract more tokens. Why is this the case? Well, in bitcode, strings are only present up to character, or only strings are present, meaning that single character values are just integer values or short values. So you're missing those. And even for Lisp and MJS, even though we may not cover the full tokenizer and may not extract all tokens, we are still able to extract most of them compared to the string extraction. Now, it's also interesting how many invalid tokens do we get. So things where the extraction method would say, okay, this produces a token and this token goes on to the parser, but actually this token, or this is not a real token. So the string does not produce a token and would be rejected by the tokenizer. And as you can see for CSV and ZJSON, the number of wrongly rejected of invalid tokens extracted by LFuzzer is pretty high. This is just because CSV and ZJSON do not have a tokenization phase. So this changes the behavior of LFuzzer a little bit, and LFuzzer cannot make sense of this information that it gets from the feedback loop, and then would, generate random inputs or generate random strings at this point. Also for TinyC, the number of invalid tokens is pretty high. This is because of a look ahead when parsing numbers. So when parsing numbers, you would go digit by digit until you find a non-digit character. And this non-digit character is also appended to our token, meaning that, for TinyC, we would have lots of numbers with some random character appended and classify them as a number token, which doesn't make sense. But you can also see that for Lisp and MJS, the number of invalidly extracted tokens is pretty low compared to string extraction, and this is because of error handling code and user interaction code that a string extractor also extracts. In terms of coverage, we can also improve over AFL, plain AFL, AFL with string extracted strings as dictionary, or our older pfuzzer method, pfuzzer plus AFL. And we improve with our LFuzzer extraction, and then we use AFL for fuzzing. And what you can see is, so the second vertical line induces when LFuzzer switches from learning to AFL. And at this point, you can see that AFL then very fast grows the coverage and can find more and more inputs just because it has more seeds and more tokens to play with. So it can mutate and rearrange those things and then cover more code in the end. This is representative for the other tools as well. So the graph mostly looks similar. To sum it up, complex input structures need syntactic fuzzing, so the fuzzer needs to know how to fuzz. We can do this with LFuzzer. We can extract tokens and samples, use them for other fuzzers to make them even faster and boost them. And yes, then get more coverage, better and cleaner dictionaries and sample inputs. And if you want to get your hands on, there is some Docker container at GitHub where you can work on. Thank you for your attention, and I'm happy to take questions.
Right, thank you, Björn. We do have a couple of questions in the chat. So the first one is from Marcelo Damorim. And the question is, can't existing black box techniques can be used to learn grammars from successful and unsuccessful examples and drive to fuzzers?
Depending on what you mean. I mean, yes, there is, I think Clade is a black box approach, which more or less does this. but still you would need valid and invalid samples. Well, invalid samples isn't too hard to generate, to be fair, but those valid samples might be hard to generate. And this is where Alfuzzer can help, actually. So Alfuzzer could generate valid samples and then give it to some approach that can make more sense of the input format in the end. I hope this answers the question.
I think it does. If not, there's I see there's a thread going in the Slack room right now. So that's the nice thing about having Slack on the side. Like, please feel free to continue this discussion after the talk.
Sure.
So let me go to the second question by David Trabisch. Can the approach be applied to any parser, or it relies on a specific structure of the program?
Yeah, that's a good question. We always get this. It does only apply to recursive descent parsers, not to table-driven parsers. The question or the answer why we chose this is simple. Table-driven parsers usually have a grammar from which the table is then generated from. You wouldn't write a table-driven parser by hand. So that's the reason why usually, so if you have a grammar for the table-driven parser, then use this grammar for fuzzing. Don't try our approach at this point. Our approach is designed for if you do not have a grammar for your specific program, which happens quite often, actually, even though you might not think this.
Thank you. There's another question from Michael Pradel. What would the main hurdles for applying this idea to larger subject programs, such as widely used compilers?
Mm-hmm. So one thing is, well, as I said, we use heuristics to find out what is tokenization and what is not. And the more complex the program gets, the more magic happens in the background. And yeah, this might fool our heuristics at some point. Same holds for those concrete comparisons that we extract. You might get more and more noise at some point. And then you need to filter this out. So you need to dig deeper. You need to find out what causes the noise and then adapt our technique, which can certainly be done, but yeah, let's see how this can be done in the future. It is definitely some part of the future work.
All right. I see the discussion is continuing on Slack. I'd say keep it up. Let's thank the speaker again. This is the end of this session. We will be back after a short break at 12:10 with a session about symbolic execution and constraint solving. All right. Thanks, everyone.